You're always ready, Jalal. Okay, we start? Okay, perfect. Thank you, Katerina Jesus, for the setup. So welcome everybody to the sixth graduate training school in KIOS. So we have the utmost pleasure to welcome Jalal Kazempour here from DTU. He's a close colleague and friend as well. So thank you, Jalal, for coming. It's really a pleasure. I'm sure we're all looking forward to your presentation today and tomorrow. So Jalal is doing one session today and one tomorrow morning. We start very briefly with the bio and then just an outline on Jalal's presentation. So Jalal Kazempour is a professor now. Congratulations as well. He was recently promoted in DTU at the Technical University of Denmark, DTU Department of Wind Energy Systems, in short DTU Wind. So Jalal is currently heading the Section Energy Market Analytics, EMA, with 10 plus research staff. He's also the head of studies for the MSc program Sustainable Energy Systems, which is one of the flagship and most attractive MSc programs of DTU. Regarding his research, Jalal is interested in data-driven and market-oriented approaches to policy operation and planning, also in coordination with other energy systems, hydrogen, gas, heat, and so on. And his focus areas in the intersection of multiple fields, including optimization, game theory, control, and machine learning for energy applications. And he's currently serving as an associate editor for Info's operational research. That's just a very brief bio of what Jalal has been up to the last years. So with regards to his presentation on electricity market design bidding strategy. So in the first day, we'll focus on the market design problem. This includes the market principle, pricing schemes, how to write the market clearing problem as an optimization model. And we'll then move on to equilibrium and equilibrium model, proving the existence basically of desirable economic properties. And Jalal will discuss various energy markets in Europe, US, etc., and argue their differences. In the second day tomorrow, he will go on and discuss the bidding strategy problem from the stakeholders' perspective, so covering holistically the problem, particularly focusing on selling flexibility services of the transmission system operators, resulting optimization problem under uncertainty. We'll discuss basically real-world application, explore how to optimally solve the resulting bidding optimization problem. Jalal's slides are available also on the website. He very kindly shared the slides on Saturday. So if you want to load them now on your laptop, if you haven't already did, they're very, very interesting. So he starts setting out the scene very nicely, moving to very advanced material. So we're really looking forward. We'll see that, yes. So thank you very much, Jalal, and thanks once again for coming.
Thanks a lot. Thank you, everyone. Thanks, Matthias, for introduction, and also Matthias Stelios, who's not here, but Stelios, if you will hear me later in the recording, thank you for inviting me, Matthias. Andreas, Lisandros, all of you, thanks a lot for inviting me. It's really nice to be here. I love traveling, and it's my first time in Cyprus. Fantastic city. I really love it. So thanks a lot for having me here. Yeah, my name is Jalal.
You brought the weather of Copenhagen. So.
Yeah, well, no, we don't call it rain. I mean, you have to come Copenhagen to see what rain means, or wind. Very nice. So today and tomorrow, as Matthias said, we will talk about market from system perspective, energy markets, electricity markets. But what you learned today, also you can easily extend it to other energy carriers, gas market or heat market, which we have it in Denmark, or hydrogen market, which are coming, hopefully in Europe soon. So we'll talk about the principles of market. We'll start from scratch, and then we'll talk a bit about what we should care about when we say, okay, we'd like to design a market in Cyprus for, I don't know, hydrogen, for wind, for power, for gas, for whatever. So we have to see what important aspects we have to care. And then, so 3 lectures will be about market. And then the last lecture will be from stakeholders' perspective, how different stakeholders, they can optimally fit in the market, right? So we'll have just one example. The way I really like to have the lecture is interactive. So please I may ask a lot of questions from you, so feel free to be active and challenge me, please. And that would be nice to have interactive discussions. And the same goes for people online. Thank you for joining online. I have a big chat box in front of me. So please, whenever you have any questions, you don't need to wait. Also for you attending in person, whenever you have a question, just raise your hand, ask your question. If it's a long question and discussion, you can keep it for the end of the session. Otherwise, just ask. If you miss something, then you may miss more things. It might be a cascading problem, right? So ask questions right away. And also for people online, please write your questions in the chat box. I'll see that. I will answer. If I miss it, Christos will notify me that there is something in the chat. Okay. Do we have an agreement? Cool. Okay. So first questions. How many of you knows about basics of electricity markets? Raise your hand. 1/3. You are humble, not raising, or also, well, now I'm just raise your hand. Good. How many of you knows? Yeah, sorry for people online that I'm not asking. Yeah, so we have some restrictions here for online people. But I guess that people here also, they kind of represent the statistics of the online. What about how much you know about optimization? I mean, knowing means that you had a chance to code something, yeah, an optimization problem, run it, and get some solution. How many of you? Also, Christos, you. Okay. Well, that's going to be. And then, okay, what about optimization as a theory? For example, you know how to derive dual problem, an optimization problem. 3, 4. Okay, good. For many of you that you didn't raise your hand, hopefully you will learn something. If you raised your hand in all my questions, I'm not sure how much you will learn. New things. You can, if you want, you can link already. You know. How many of you know that you are a good programming person? I mean, either in Julia or Python. Well, what about the rest? I think if you are in this field, you have to be a good programmer, right? But how many of you are using Julia? 1, okay, for Julia. Python. Okay, cool. Good. I'll say it. Yeah, there's a question. And MATLAB. Okay. Well, how many of you are using MATLAB? Okay, good. Okay, MATLAB is good. I'm not against that, but maybe you have to move on. It's a good thing. I did my PhD with GANs. I don't know if you heard of GANs. Have you? Okay, just a few of them. Well, the young generation, they don't know what GANs is. But you have to move on, right? And learn using. Good. Fantastic. Today, the first lecture will talk about market clearing as an optimization problem. Very easy. Then I'll try to make sure that all of us, we are in the same page as what optimization problem is, what different aspects of optimization problem, and how we can use these principles for market clearing. Okay. Cool. And hope for people online, everything is fine. They hear me well. And maybe you can write something in chat box so I can make sure that you will have the option to write questions on it. You can write hi in the chat box. Anyway, okay, let's start. Yeah, I see a thumb. Good. Okay, a very simple question, simple example. No transmission line at all. We have one generator only, capacity 100 megawatt, offer price $12 per megawatt hour, and we have only one load, 80 megawatt maximum load, bid price. Bid price means that the maximum price that the demand is willing to pay for buying 1 megawatt electricity. And the same for generator. That's the minimum price that this generator is willing to sell, right? At that price. By the way, coming from a game theory community, I will use she and her in pronouns, because in game theory, whenever you are irrational, they are she, right? So I will use that. Yeah, I will use that more often. Okay, Simple question. What will be the production level of G1 if you are the market operator? What will be the production of the generator? Yes. 80. Why? Why not 0? Because the offer price is lower than the bid price. There is an agreement there, of course. Consumption level, it will be fully met, right? The demand. What will be the market clearing price? 12 or 40? Yeah. 12. Yeah, exactly. 12 is the offer price of the last generator dispatch, right? And here we have only one generator. Offer price is 12. So we are bidding. So the market price will be. We will later see how to drive this price. Good. Now we have two generators, right? 100 megawatt and 80 megawatt. G2 is the new generator. The capacity is a bit lower, but the offer price is a bit higher. So G2 is willing to sell electricity at price minimum 20. Demand is unchanged. Good. So what will be the productions of G1 and G2 if you are the market operator? Yeah, Lisandros.
100 from the first generator.
Yeah. Yeah.
For demand.
Yes, exactly. So, yeah, sorry, we have two demands. Okay, I missed. I was. Yes, also we have the second demand of 50 megawatt. Yeah, that's fantastic. Okay, G1 fully dispatched 100 megawatt. The second generator will be dispatched at 50 megawatt. Good, fantastic. And both demands will be fully met, right? Good. Important question. What is the market clearing price? Yeah. 20. Now the last generator dispatched, right? 20. 20 is the offer price of the last generator. Fantastic. Very good. When we say the market price is 20, you agree that it's the uniform price. If you're talking about uniform pricing, not pay as bid, it's the single price that based on which we pay generators and we charge demand. Agree? You know also about pay as bid, right? Also, we have pay as bid. If we clear market based on pay as bid pricing, then you pay everyone based on the bid she submitted. Clear? Good. Okay, let's see how we can form. I mean, the problem was easy enough for you to solve it instantaneously, but the realistic problems are not that easy, right? We need to have optimization problems to solve that problem. How we can write it as an optimization problem? So what we can do when we say we like to develop a market clearing optimization problem, we are talking about maximizing something called social welfare. Also, you may call it surplus, market surplus, subject to all technical constraints of generators and demands. So far, we don't have transmission line. We will also talk about that. And also adding power balance. Okay, what is the social welfare? Just to make sure that we are all on the same page. Have you heard of social welfare? What it means? You know? Yeah.
Mathematically, it's the surface between the ask and the bid curve.
Exactly. So let's say that this is dollars per megawatt hour, the price. This is the megawatt, right? So for example, in the previous example, we had a cheap generator and a bit more expensive generator, right? And then for demands, we had two demands, something like this. The demand that is willing to pay at high price and then a bit lower. Okay. And then we said that the market clearing price is here. That's the intersection of supply curve and demand curve. Are you familiar with this microeconomics principle, right? Supply curve, demand curve, intersection gives the price, right? Very good. So where is the social welfare here? Exactly. Why? So I'm hearing here that the social welfare is the area between these two. Can you tell me why? Why do we call it social welfare? Why is it interesting for us that we like to maximize? Right? That's the most fundamental question of the market. Why should we maximize? That's a very good answer. So the answer here is that both sides, generators and demand, they are both happy. Can you elaborate a bit more why they are both happy?
Because generator side can earn more.
That's good. That's correct. But let me also reward the question, the answer. So this is the area, the whole area that I'm putting here. It's what demands are willing to pay max, right? On the other hand, the area under the generation curve, the offer curve of generators, it's their cost, right? So when we are maximizing the area between these two curves that we call it social welfare, what are we doing? At the same time that we are expanding the utility for demand, at the same time we are minimizing the cost for generators. Are you with me? Do you agree? So that's why exactly as you said, what's your name? As Sina said, when we are maximizing social welfare, then both sides, generation side and demand side, they are both happy. Clear? Good. So we like to maximize social welfare. What is that? It's the total utility of all demands. It means the curve, the area under demand curve minus the area under the supply curve, the generation side. And this minus means the area between two curves. Clear? Good. Okay, the constraints, technical constraints, for example, how much a generator, to what extent can produce. The capacity constraint, the same for demand, how much the demand maximum is willing to buy. And then power balance equality, means that the total demand is equal to total demand. Clear? Great. Good. This is the market clearing problem as an optimization problem. For the example, with two demands, two generators, we solve together. Could you please look at it for 30 seconds and try to think what this optimization problem does? What are we doing? Can you volunteer to teach, to explain? Someone here. Sorry, I forgot your name. Theodore. Okay, I'll get back to you, but let me find some. Maybe from that area. Okay. I don't want to put pressure, but anyone new would like to explain what this optimization problem does? Let's just start with, yeah, Andreas, yes.
Finding how much.
Tell me if we start from, no, start term by term.
We're trying to.
Okay.
By using.
What is the first term?
It's how much the demand is willing.
Okay. 40 is the utility price, the bit price of demand one, and PD1 is a variable. It's listed under the maximization operator. It means how much demand one is will consume. Very good. And the second one is the same for demand. Good. What is the second term?
It's always for the generator.
For the generators. The 12 and the 20 is the offer price of two generators. PG1, PG2, they are variables, decision variables. How much every generator will produce. Remember always to list all the variables, primal variables, under your minimization or maximization operator. Please do that. Always. Okay, what are the four constraints? The first four constraints? Andreas?
It's how much maximum demand.
Yeah. The maximum demand and maximum generation. Between 0 and their capacity. And what is the last constraint? We call it power balance equality. The total demand equal to total generation. Very good, very easy. Good. Is this optimization problem convex? Do you know what convex optimization? Is it convex? How many say it's convex? Cool. Is there anyone says it's not convex? Okay, good. Let me ask first, why do we want our optimization problem to be convex or not? If you have a choice, do you wish to have it convex? Sina? Yes, you want to have your optimization problem convex. Why? Which one is your answer? Complexity or your global average? Okay, anyone would like to add? Yeah, Sandra?
The optimization problem, then it can be solved.
It can be optimally solved to global optimum, right? If it's non-convex problem, if your optimization problem is non-convex, of course you can solve it by any solver, but you cannot guarantee your solution is globally optimal. There might be another solution which is even better than that, right? If it's convex, done. You get the solution is globally optimal. You cannot find better than that. Is it clear? Okay. How do you know that this problem is convex? Anyone else? Let's start with the objective function. How do you know that objective function is convex? Is this convex? Yes, it's linear, right? Linear is always convex. If it's not linear, it's quadratic. Is it convex? Sandros?
Maybe.
Maybe. I have to check it.
Only the eigenvalues
Okay, how do you check the eigenvalues?
by calculating, or another way is like
Yeah, I heard some words here. You check what? Hessian matrix. You check the Hessian matrix. Should be semi-positive definitely, right? If it is, then it's convex. If not, it's not convex, right? Very good. So if it's linear, problem solved. It's convex. If objective function is quadratic, you have to check Hessian. If you don't know what Hessian is, please take linear algebra course or something like that, right? Or convex algebra. How do you know about constraints? How to know constraints are convex or not? It looks basic question, right? But important question. Yeah, we have a new one. What's your name? Dario. Yeah, go ahead. Yeah, they are linear and convex happy, but if they are not linear, how to know that?
check that data, but also you can check on the parameters.
Yes, but okay, if they are linear, linear is always convex. If it's not linear, if for example, instead of PD1, I have something quadratic, is it convex or not? If I have quadratic term in my constraints, is it convex? I'm just trying to challenge you to think a bit more, right? When next time you solve optimization problem, just think of it more deeper. Yes, Sanders?
For equality constraint, it has to be linear.
Exactly. When you have equality constraint like this, if you have quadratic term, done. It's non-convex, right? Done. But for inequalities, if we have like inequality like this, if we have quadratic term, it could be convex or not. What should I check? Not this, yeah. You can check for, yeah, but you can check if it admits a conic constraint or not, right? There is a specific form of something called conic constraint. You have to see if it fulfills that requirement. Okay, anyway, but what is important? This problem is linear. When it's linear, there is no two variables multiplied by each other. There is no nonlinear function like sine or cosine or something like that, right? It's a linear problem. All terms are linear, a constant times a variable or just a variable. So it's a linear problem, linear problems. We can solve it up. Good. Good. I'm in the wrong direction. Yes. Have to, I mean, you told me that the market price for this case is 20. Can you also show me by optimization problem the price is 20? How we can get price here? Theodore? dual problem. Do you want me to derive dual problem, or I can check something? I mean, if we solve this in MATLAB or Julia or Python, whatever, will you solve the dual problem again or not? Just you can ask Python to give you something. What is that something? Not dual problem, but something very close to that. Yes. Dual variable. Fantastic. Dual variable. Which dual variable? Very good. I'm writing something here after a colon, something called lambda, and I call lambda as a dual variable of the correspond of this constraint, and this lambda gives me a model. Okay, let's discuss it. Dual variable, what it means. What does lambda show? Have you heard of that dual variable? Dual variable, or you can also call it multiplier. Sorry, Lagrangian multiplier. So lambda is a dual variable for this constraint. Every constraint has a corresponding dual variable. For example, dual variable for this, you can call it mu tau. Or for this one, sorry, or for this one, you can call it mu bar. So when we have a dual variable for a constraint, what does it show? Any answer? Or people online, what does dual variable show in the optimization story? Yes?
I think it's how much the objective function changes in respect to the decision variable.
Yeah, I mean, you know it. Good. So every dual variable, for example, lambda, shows the sensitivity of the objective function with respect to any small change in the corresponding constant in the optimal form. So it means that, for example, say that your optimal objective function is 10. So if you add something very small here in the corresponding, so instead of 0, you have 0.0001. How much the objective function will change? The sensitivity. The dual variable shows the sensitivity of the objective function with respect to any small change in the corresponding constant. Is it clear? Good. Okay, that's a dual variable. If you need to know more about dual, take complex optimization course, right? But lambda, so we have how many constraints we have? We have 8 constraints here. One constraint is not 9 constraints we have. So we have 9 dual variables, but you picked only one constraint and you told me that, okay, this specific dual variable gives me price. Why that one? Why not the dual variable of this one gives you price? Why this one? Remember how we defined the dual variable? Tell me. Anyone new? Okay, Sanders, why?
Or maybe
If I add another equality constraint, for example, for storage, then you will tell me that changed market price to that. Yes. Because what? You're close. Remember how we derive the price, right? The price is the intersection of these two curves, right? So if you add any small change here, it means that you are changing this point either by shifting the generation side or demand side, right? For example, if you increase demand or whatever, you're just shifting a bit the demand side. So actually, I mean, lambda is the sensitivity. It shows how much objective function changes if your demand changes a bit. That's the point. So there is a reason why we pick lambda, dual variable of the power balance equality, as the market. Because it fits with what we want. We want to see how much social welfare, our objective function, is being changed if we introduce a small change in the demand. Do you follow me? Agree? Everyone is agree? Agree? Yeah. Okay, cool. Fantastic. So we discussed about dual variable. So again, all the things I'm talking about is when you use uniform pricing. There is one price for everyone. If you use pay as paid, different story. If you use something different called Vickery-Clark rule, it's a different type of pricing. Yeah, then the price will be good. So we discussed about dual variable, lambda, why it's the price. We discussed what dual variable shows in general. Oh, about the sign of dual variable. Do we know anything about the sign of lambda? Will it be a positive value, negative value? Will it be zero? Do we know? So since this is a dual variable corresponding to a quality constraint, lambda is free. It means that it can take any value. But for example, dual variable for this one, since it's corresponding to an inequality, it's always non-negative. It could be zero, it could be positive, it can't be negative. Why? Again, you can take convex optimization course. There will be a lot of these. So by theory, can lambda be negative? Can price be negative? Yes. Right. We can discuss later if you want when price becomes negative. Good. So this is the compact form of market clearing as an optimization problem without any transmission line. So just instead of saying two demands, two generators, we write it in a generic form. So could you please check it for a few seconds and see if it looks like correct? Well, there's no question on that, right? How many people do you have? 15. Good. Does this generic formulation make sense to everybody? Would one of you explain it in some seconds what it is? What objective function is, what constraints are? Someone? Objective function, what do we do? Exactly. So what is D? Yeah, but what is this D? What is the index D? Yeah, it's an index for demand, right? For example, you have one per demand. So you can say D is the index of the D. For example, D runs D1 and D2 in our case, in our previous example. But you may have millions of demand. Right? And similarly, G is an index for generators. For example, in previous example, G runs G1 and G2. You may have more than two generators. Yeah. So the sum of utilities from demand and the sum of the cost of all generators. So very good. What does this sign show? For each demand. Okay, for each generator and very good. So if I have 5 demands and 10 generators, how many constraints do I have? How many constraints I have here? Yeah, but I have upper bound and lower bound. So how many? 10 constraints here. How many constraints here? 20. How many constraints I have here? 1. So you have 31 constraints, right? So your number of constraints are 2 of D. This is the cardinality, number of demands, plus the number of generators, plus 1, right? Number of variables, they are here. You have number of generators plus number of demands. Is it clear? Okay. So now let's talk about network. Now we like to add a network. The same problem exactly, 2 demands, 2 generators, but they are connected in different nodes, right? I don't know, this could be Nicosia, this could be Limassol, this could be Larnaca, so different places. So let's say the capacity of every line is 100 and susceptance is 500 Siemens. Good. Let's see that how we can extend our market clearing optimization problem. Well, I don't know how many of you knows about AC power flow. So how many of you took any course on AC power flow? Well, every power engineer should know that, right? It's like our bike. Everyone should knows how to write AC equation. In the market clearing problem, do you suggest me to write AC equations as they are? You're laughing, Dario. Why not? You're not laughing. You're smiling. Why? They are very ugly. Okay. I mean, we don't care if they are ugly or not. Why not to put them? They are non-convex. They are non-convex, right? They are non-convex. Why they are non-convex? Yeah, they are non-convex operators there, and they are also product of two variables, right? Very good. So, have you heard of DC power flow? Have we do a lot of horrible approximations to end up to this, right? So if you haven't taken any courses on AC/DC power flow, please do that. So what it says, after a lot of approximations, I can come and teach for 2 hours what kind of approximations we introduce to get to that. It says that the power flow between node N to node M is equal to susceptance, is a physical parameter, is the susceptance of that line, times theta N minus theta M, the phase angle in bus N minus phase angle, a voltage angle in bus N. Right? Is it linear or non-linear? This linear. Remember, it's a quality constraint. We can't afford any non-linearity there, right? Every term should be linear, and this is linear. But I don't want to talk more how bad this approximation is, but well, that's what the people they use for market clearing, also in industry. Good. So please look at this optimization problem now and tell me what extra things have been added to previous optimization. Let's check it for a minute. Okay, let's start. Let's start one by one. Let's say starting from maximization. It's the same as before. But is there anything here changed? Anything? Yeah. Yes, we have 3 more variables, thetas. They show voltage angles in different nodes. Very good. Objective function, is it the same or changed? It's the same. Very good. The first 4 constraints, the same or changed? Same. Good. What about this 3? What are they? Power balance in every node. So instead of having 1 power balance, now we have 1 power balance per node, right? So how you can see is as following. So if I get back to previous here, so you have to write 1 power balance for each node. 1 power balance here, 1 power balance here, 1 power balance, right? So you can say that, okay, I have a generator here, I don't have a demand, but then you have to say what direction you want to consider for your flow. For example, here you can say that this is flow from bus 1 to bus 2. This is flow from bus 1 to bus 3. So if you write equality here, power balance, it will be PG1, that's your production. Those power flows, they are going out of the node. So they are like demands. So it's minus F12 minus F13 is equal to 0, right? And of course, instead of F1 to 2, you can write B of 1 to 2, the susceptance, theta 1 minus theta. Okay. So how I know in advance that the flow, okay, here you have only one generator, but here, for example, you don't know. How I know in advance that the direction of the flow is going out? Why it's not opposite? How can I know it in advance? Do I know it in advance? Sandra? I don't know. So if I put the direction wrong, then I'm dead.
The variable is positive, then you get the correct direction. Otherwise,
Exactly. We solve the optimization problem. If the value for f is positive, it means that luckily the direction is the same as what we saw. Otherwise, if it takes negative, it means that the direction is different. Right? So it doesn't matter what direction you consider, and then later when you solve the optimization problem, you will see what the direction is based on the sign of it. Good. So that's what we did here, right? So in generator, in node 1, we have the generation minus 2 flow going out of that node. And the same for others. I mean, so here is theta n1 minus. So that one goes to here. So you can write either plus theta n1 minus theta n2 or also minus or n2 minus n1. So you can play with this stuff. What about the last three? Not the last. Those three constraints, what they are? Line limits, right? Very good. So this is the flow between 1 and 2. It's 100 and minus 100. Do I need to put this one minus 100? Do I need that? Yeah, I need that, right? Why? So because the lines could be, the direction could be, sorry, I have to, yes. Because the direction could be wrong, the opposite side. So we limit the flow between capacity and minus capacity. And what is the last constraint? Yeah.
because you have a connected graph, have a negative value at 0, and therefore there is a linear space where the
Very good.
and therefore
One good explanation. Any other? It's a reference node, right? It's a reference node. You have a unique solution for the differences of the thetas, but not for each of them. You have multiple solutions. What is the unique is their difference. So when you put one of them equal to 0, then the others takes also 0. Okay, that's also all about DC power flow. You can learn it in a different course if you want. But this is the generic form of market clearing problem when you have also transmission. Can you check it for a few minutes and see if you can interpret every single term? So now in variables, we have theta n, 1 voltage angle per node, n. N is the set for nodes. So for example, it could be running between node 1 to node 24, for example, right? The objective function is the same as before. You have demand and generation constraints as before. You have one power balance equality per node. And the corresponding dual variable is lambda n. You have one price per node. And then the total demand in that node. So this is the demand, the set of demands in that node, total demand in that node, plus all the flows that going out of that node from the lines that connected to node n, minus the total generation in that node is equal to 0, right? Then we have the transmission line limits for every node, the lines. here, I mean, in our case, we say that, okay, we have line everywhere. But if not all lines connected, then you have to say, for example, all just for N and M if they are connected. And then the reference. Very good. So how many primal variables we have? Number of generators plus number of demands plus number of good. Yeah, that's it. So we can also discuss that why is it possible that lambda n might be different for different nodes? Yeah. When does it happen, for example?
Lines are congested.
When the lines are congested, then the nodes might. The price is not. Very good. Let me ask a few questions. Is this the way we clear the markets in Europe or US? Let's start with European markets. How do we solve the European markets? Here. Sorry, I'm sorry. No, it's so. Is it the optimization problem that we solve when we clear the European electricity market? Yeah, are you? So what Dario says is that we don't have locational prices. What? For clearing. Okay, it does mean that do we have one price for whole Europe? For zones. Okay, in Europe, what happens, that's the different, of course, I can comment. We have 20 something bidding zones in Europe, right? 20, how many? 20 something, yes. So, yeah. How those bidding zones have been defined, it has its own story. So, for example, in Germany, how many bidding zones we have? Only one. So it means that the whole Germany gets only one price. In Denmark, we have two bidding zones. In Norway, we have 5. Right? So what happens is that in every bidding zone, we have right one power equality constraints like that, our balance equality, right? So we have one price, not per node, but per zone, per bidding zone. Very good. So then this constraint, well, we don't have thetas, but flows between zone Z and Z prime, not F, but it's ATC and minus ATC that the TSOs they define. But now we have also something more flow-based coupling, so you add more constants. So that's how. So here it means that the generators they submit their bids. Yeah. Do we know what options, bidding options, suppliers and demand they have in Europe? Is it only this, submitting a bid, a price quantity bid, or something more? Peter?
I think we have multi-step hybrid, local orders, local orders.
We have more complicated system than this in European market. For example, the generators, they can bid something like this. So for example, this is for hour 1, this is for hour 2, this is for hour 3, right? And saying that, okay, I'm selling at the average price of X, something. Do we know why European market lets bidding something like that? It's called block orders. So when we add block orders, then the market clearing problem is different than this. Not very different, something on top of this, right? So why do we have block orders in European markets? Have you heard of that? Someone else here? Yeah, Sanders?
Because of the operational constraints of the generator.
Yeah. There are a lot of technical constraints that generators they have. Have you heard of unit commitment? I heard you developed something for Cyprus. TSO, very good. So conventional units, especially, they have technical constraint, right? I don't know, ramping, minimum uptime, minimum downtime, or something like that. Do we include them in market clearing, European market clearing problem? No. In Europe, we don't put unit commitment constraints there. But we ask generators to internalize their technical constraint in their bids. So they internalize their constraints here. Right. Sorry that I'm just teaching everything on surface just to suit you different. So hopefully after this lecture, you have different things to go and so, but I don't go much deep, right? Very good. So how is the case in US? In US, is this problem being solved? Or not? Something different. When I mean, can you name a few electricity markets in US? Yeah. KIOS is the ISO system operator in California. Well, more. PJM, Pennsylvania, New Jersey, Maryland market. Any other market? Yeah, Texas market. What's the name of the market? ERCOT. It's a very special market. How we cannot again explain half an hour. Done. Good. But are they solving this optimization problem or a bit different? Yeah. Yeah, they include unit commitment problems here. So I'll talk a bit about that in lecture number 3. But also they add unit commitment constraints. So a bit more extended versions. Anyway, the basis of market clearing optimization problem is this. But it's not exactly the version that the industry uses, but the foundation is here. Very good. Okay, I like to, yeah, let's challenge you. So this is the optimization problem for market clearing. Hopefully now you agree, it looks okay. So what is this one? No, not this one. Yeah. So Ugur asks, is it likely Europe will move to nodal pricing in the near future? We can discuss it. We can debate. So yeah, so we discussed that in Europe, there are like 20 something zones. The question is that, oh, by the way, in US, there is nodal market clearing, so there is one price per node. So the question is that, is it likely Europe will move to nodal pricing? I think it's more a political decision, to be honest. And if you want my opinion, I don't think there's a right or wrong answer here. I would say no. I don't think Europe will. But there are a lot of debates there. Good. So this is the market clearing problem we discussed. What is this one? What is this one? Is it the same problem? Yes. It's the dual version of that problem. So in convex optimization, every optimization problem that you can call it primal problem, like the market clearing problem you have, it has a twin sister that we call a dual optimization problem. Right? And if the underlying problem is convex, these two problems are equivalent. Is it clear what I'm saying? So this optimization problem that you see in this slide, it's the twin sister of the previous optimization. We call it dual. So how to derive it, we will discuss. I will challenge you. But tell me, in this optimization problem, what differences do you see? What features do you see here? What differences do you see? Yeah, Alessandros, you can start.
The primary maximization problem.
Now it's a minimization problem. Okay, that's the first difference. Any other feature, any other difference do you see?
W is variable.
Very good. The list of variables are fully different, but do they remind you something? What are they? Let me get back to previous problem. What are they? This is the prime original problem, right? This does. Yeah. Yes, you parameter varies. Parameter is a fixed value. You see dual variables of the primal problem? Yeah, you see, these are the dual variables, right? So I listed primal variables here, but the dual variables here. Now see the other problem? Now dual variables are here. What are the dual of dual problem? You see, now the dual of that problem are our original primal variables. Interesting. So you can ask me that, okay, what the hell? Why do we need these things, right? Later you will see that in many discussions, analytical discussions to prove properties of market design, or I don't know how theoretical you are when you write your paper, you do your analysis. I mean, deriving the dual optimization problem is a good friend of you. It helps you a lot to understand the properties of your problem. So it's always good to know how to derive your dual and see if, for example, you can't prove in your optimization problem directly, maybe you can prove that in the dual problem. And since they are twin sisters, if you have some property in the dual domain, you will have the same property in the primal one. It gives you more degree of freedom to investigate it, right? I will give you as an exercise for you to derive this. I will tell you how to derive dual problem in general, but then I'll ask you as an exercise to at least check it and see if you can derive the dual problem as it is. Okay? Deal? Okay. I see still we have 25 minutes. Usually I give breaks, but I see that it's 25. Do you agree that we continue for 25 minutes? Are you tired? Are you okay? Good? Okay, fantastic. Okay. My first lecture as the power system part is done. But now I like to teach you a bit from optimization theory, right? So for the next 26 minutes, you will not hear about power systems, but more on Good. So how to derive the optimality conditions and dual problem of a linear optimization problem. I mean, I promise, eventually, if you stay in this field, you will need this at some point. So good to learn it today, at least some basics, okay? If you're not familiar already. If you want to buy or to get a Bible in convex optimization, this is the book. Right? But if you like to get to read some easy text adapted for engineers, I think this is a good. Okay. Do you know him? Who is that? It's this guy, right? Stefan Boy. He came to you a few years back. You can read about his statement. DTU should teach a course on convex optimization. Why? The interesting part is the next. All students should be obliged to take it. All students. To be honest, all my PhD students, they are obliged. So I think it's a very good idea. So if you are looking for some courses or if you have to take some convex optimization, I don't know, is it, do you have a course in convex optimization here? in this universe? No. Sandra, you have to start new. Good. Yeah, I put it though it's a bit too strong, but I agree. What I wanted to say. Don't say that I'm power engineer. Who cares? No, important. Well, if we have this optimization problem, a generic optimization problem, the only variable is x, minimizing f of x. It could be anything, but linear. Let's say. Two type of constraints: equality constraint, h of x equal to 0, and j of x is lower than or equal to 0, with a dual variable of mu. Right? It's a generic form. We call it, it's in the standard form, or it's canonical form of optimization. Why? Because it's minimization, and inequality is lower than it. So the first things, whenever you work with your optimization problem, if you like to work KKT, I'll talk about that, or dual problem, you have to formulate your problem in this form. If it's maximization, multiply to a negative, to a minus, then it's a minimization. And the same, so if you have a constraint greater than or equal to, multiply both sides to a minus, then the sign will be, right? So always prepare your optimization in this form. Then, this is something that we call Lagrangian function. It's a function of primal variable and the dual variable. It's f of x plus. So if you have a vector of constraint, that's why we have a transpose. If you have only one constraint, it's only one constraint. If you have 5 constraints, for example, equality, you have to put all of them, right? It's like a vector. So lambda times your quality constraint plus mu times your inequality. So for example, let me give you an example. Let's say that we are minimizing, I don't know, 5x plus y, x plus y is equal to, I don't know, 6, 2x minus 3y is less than or equal to 7. I don't know if it's even a feasible problem or not. But if you want to write the Lagrangian function, let's say the dual variable is lambda, dual variable here is mu. Can you tell me what the Lagrangian function will be? And one of you help me? I see. Yeah, tell me. Very good. What should I write? Plus or negative? What's the next thing should I write? Plus, yes. Lambda. Very good. Yeah. Very good. That's your Lagrangian. Is it clear? Right. So now you have your Lagrangian function. This is your optimality conditions. This is your optimality condition. So when you like to solve this problem by hand, okay, if you have a problem like this, like what we wrote together now, how you can solve it? Do you write it in MATLAB or Python and ask it to give you a result, or you can solve it by hand? How can you solve it by hand? You need to derive in the optimality conditions that we call it Karish and Tucker, in short, KKT conditions. So how to do right is that. So the mission is that this is an optimization problem. We need to get to a system of equations. You remember we learned system of equations when in primary school or something like that, right? So we should solve this problem. This problem you can solve it by hand, right? Okay. So what we do is that we have this Lagrangian function. With respect to every variable, you take a derivative equal to 0. We call it a stationary condition. Then every equality constraint, we repeat it. Remember I told you that lambda is a free variable because it's dual variable of the equality. The mu is non-negative because it's the dual variable of the inequality. You see it's here. The primal constant, I mean, this original problem says that j of x is lower than or equal to 0. Look, I wrote it here. Just if you want, you can keep it as I wrote. So it's j of x is less than or minus j of x is greater than. It's the same thing. So far everything is clear unless this one. What does it show? What does it say? Yeah, Andreas?
Q of x times mu.
Yeah, you call it complementarity constraint. It says that mu times j of x, either if you even if you put the minus, it will not change, equal to 0. You can have this negative or not. Doesn't matter. Okay. So either you can write j of x is non-negative, mu is it's non-negative. J of x is lower than or equal to 0, and their multiplication is equal to 0. But since we like to have a symmetric sense, we can write it in opposite way, just to write it working. So it's the same. Is it clear? Okay, let's the example that we had it here. So if we like to write the KKTs, what will it be? Remember, it was the derivative of the Lagrangian function. How many variables we have? Yes, please. Yeah. Yes. It's what? This one? Yeah. Yeah. Either j of x is non-negative. It's the original constraint, right? Or you can say minus j of x is greater than or equal to 0. It's the same sense. So I wrote it in that way. The right side, also this one. Yeah, it's correct. Always mu is non-negative. So this constraint is the combination of 3 constraints. This means j of x is lower than or equal to 0. It says mu is non-negative, and it says j of x times mu is equal to 0. Clear? Okay. Can you, okay, how many primal variables I have in this problem? 2. So I have to write derivative of Lagrangian with respect to x and with respect to y. Right? Can you help me? So whatever they are, it should be equal to 0. Can you help me to write this part? Derivative with respect to x. We have x here, we have x here, we have x here. So what should I write here? Fantastic. What about here? Clear? And then the first one, x plus 1 minus equal to 6 is the equality. Inequality says 7 minus 2x minus 3y. Yeah, it's greater than or equal to 0. The corresponding dual variable is mu, which is non-negative, and their product is equal. Is it okay? And if you want, you can also write that lambda is a free variable, just for information. Is it clear? Good. So I have another example here. So why I did this, because now you can solve this problem, right? You have a set of conditions, and you can, as we learn in school, wherever, we can solve this problem. And the solution for this problem is the solution for this. Is it clear? Very good. So let's drive linear optimization, the KKT for this problem. What should we do? The first things? The first thing is that you see we have to put it in a canonical form, right? That's the first mission. So we do here. I directly derive the Lagrangian function from here, right? Remember here we have minus because you flip the equality, right? To be in a canonical. So do you agree that this is the Lagrangian function for this? As I said, first you need to flip the inequalities sign by multiplying to minus. Do you agree with the Lagrangian function? Good. And then you see we have 4 variables. So you have 4 derivatives equal to 0. You didn't have any equality condition, but you have many inequalities. So for every single inequality, you have a complementary. And this is your optimality condition. So if you solve this problem, this set of equations, this system of equations, it means that you solve the original. Clear? Yeah, next lectures you will see why I'm talking about KKT's dual problem. They will have some meanings when we clear them all. Right? Just stay with me. So I'm not a mathematical teacher, right? Good. Yeah, let me move. So let's talk about it, the last 12 minutes, how we can derive the dual problem. So we derive the KKT. So I'm talking about 2 different things. Optimality conditions, a system of equations that you solve it by hand. Now also I'm talking about dual problem. Remember your exercise, if you want, is this, right? This is the dual problem of the market clearing problem coming from here. So the mission is that from here, we want to reach to here. And the question is how? Good. Oops. So now in the next 10 minutes, I will teach you how to derive dual problem. Again, that's another fantastic tool that helps you a lot with interpretation of different things. Good. Remember, we derive the Lagrangian function, right? So now we need to derive something called dual function, not problem, dual function. And dual function is minimizing the Lagrangian function over the primal variable. So we minimize the Lagrangian function, which is a function of x, lambda, and mu over x. We call it dual function. Fantastic. So if you solve this problem, your lambda and mu, they are uncontrolled, right? I mean, you are not optimizing over lambda and mu, only over x. So your solution will be dependent on lambda and mu. So what happens is that when we want to derive the dual, we say that, okay, also now this problem, what it is, now we maximize it over lambda and mu. Is it clear? So the inner problem, this problem is a function of x. So we treat lambda and mu as parameter. And now there is another maximization problem that we maximize lambda and mu. So if you take an optimization course, or I don't know, if you, for example, watch this video, they will explain you why we are doing this. But a very simple explanation is that if, for example, our convex optimization is this as a function of x, then by maximizing dual function over mu and lambda, we are trying to find the dual problem whose maximize is the same as the minimum point of the primal problem. Is it clear? Oh. So here again, I'm just here to teach you how to derive the dual. So as I said, we minimize the Lagrangian function over the primal variable and then maximize over the dual variable. Let's go for example. So this is our Lagrangian function, right? So what happens is that we are minimizing the inner problem over the 4 primal variables. This is my Lagrangian function. And then we maximize it over the 6 dual variables. Are you following me or not? Is it clear? Is it? Okay. Good. So if you solve this problem, you have the dual problem. Have one maximization here, one minimization. So if we can get rid of this minimization problem, then done. We have the dual problem. We have a dual problem of the maximizing only over the dual problem. Sorry, dual variables. How to get rid of this minimization? The question here. How? Yes. Drive the KKT conditions of the inner problem, right? When I say inner, this is the inner problem, this is the outer problem. So what Lissandros tells me is that derive the KKTs of this problem. Remember, KKTs are just a set of constraints, conditions. There is no minimization, maximization. Good. Do you have any constraint here? No, you already brought all constraints. So this is an unconstrained optimization problem. So we learned it in high school, right? When you like to maximize something, take a derivative with respect to variable equal to 0, done. There is no constraint here either. Very good. So you can derive the constraints, the KKTs here. So here you will have 4 equalities, 1 per each of them. So blah, 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 something. Okay, let's write for x1, for example. For x1, it will be 80 minus 2/3 mu1 minus mu2 minus mu3 equal to 0. That's 1 KKT. Okay, you can write 4 of them, 1 per one. Okay, so then you will have 4 constraints here. I agree. So maximize with 4 constraints. But what will be the objective function of the maximization problem? If I take the KKTs of this problem, am I done or not? Something left. Is my question clear? Let me show you. Here I have -1 times minus mu1. Is it a variable of x1 or x2 or x3 or x4? No. So what should I do with that? Yeah, let me leave it here as where it is. So then you will have mu1 -1 times minus mu1. Here you have plus mu2. That's it, right? Yeah. So you have 2 terms here, mu2. You have 2 terms here, and then the rest goes to the 4 constraints you have. And now this is a variable, sorry, objective function for maximization. So what happens is here. This maximization is the same maximization. The 2 terms that I said, I left it here. Now all the KKTs I took from 4 variables, I put them here. Is it clear? This is my dual problem. The original problem was minimization. Now it's maximization. My only variables are my original dual variables. There is no x1 to x4. Yeah. So this is the dual problem of the original primal problem. So I'm going next. So this problem and this problem, not this one, sorry. Let me go, yes. So this primal problem and this dual problem, they are twins. They are brother sisters. You can solve either of them. They are equivalent. And hopefully in the next 3 lectures, or especially 2 lectures, I will convince you. Having this knowledge, having these tools in hand, they are very nice. It will give you options to prove many things. Okay? There are a few details that I want to skip, but you can read the slides. But you got the main point. So the last things that I like to tell you, a few things, is that the number of variables in primal problem is equal to number of constraints in dual problem. That's clear, right? And the other way, right? Dual problem of the dual problem is the primal problem. Dual variables of dual problems are primal variables, we discussed before. What is important is that not in the optimal point in general, the objective function of the primal problem is greater than or equal to the objective function of the dual problem. In the optimal point, that's something we call it a strong duality. The primal objective function, so this stars means optimal. So the primal objective function is equal to dual objective. This is again a optimization theory or property that you will use a lot if you go to a market study. It gives you a lot of knowledge, a good tool to prove many things. Is it clear? So, how long is our break? 30 minutes. Okay, I don't expect you to drive the dual of market clearing problem in 30 minutes, but you can have some thoughts if you want. You can talk with your friends, and also you can have it for tomorrow if you want. So remember, this is market clearing problem, and we did the same magic pitch here. That's the dual problem of the market clearing. If you are a market operator, you can solve either of the optimization. Clear? So maybe you can tell me tomorrow or whenever you want how we drive this. Tell me if this equation this formulation is correct or not. Maybe it's wrong. You can. Good. Yeah. So next lecture in half an hour, you will see the first application of why I taught you about all this. Okay. See you in half an hour. Hope you still have a lot of energy to learn a few things more. So last lecture, you learned about market clearing as an optimization problem. Also, you learn very quickly how to derive optimality conditions and dual problems. Hopefully, I will convince you that, okay, learning those things are good. So this lecture, I want to talk about market clearing as an not optimization problem, equilibrium problem. First of all, is there any of you knows what equilibrium problem is? Anyone raising hand? Equilibrium problem? None of you? Okay. But before that, I like to spend like 10 minutes on European markets and to make sure that we are all on the same page how different markets exist in Europe. Of course, also we can discuss electricity markets in US, in China, in Australia, but well, let's more talk about Europe. So next 10 minutes, I'd like to talk about that. Then I'll be back to equilibrium problem. Okay. Good. So let's say that this is what's the problem with that? Okay, I have to stop sharing. Sorry. And give me a minute, please. Okay. Oh, I have to enable it. Yes, it works. Back. So, sharing slides. Okay. That's good. Yeah, we like to talk a bit about markets in Europe. So let's say that this is time, right? Tell me what European markets, what different markets do we have? So the most famous one is, thanks. The most famous or important one is day ahead market, right? So let's say that this is a day D. When do we solve the European day ahead market? Yeah, Peter?
It's D-1.
D-1 at what time? Usually,
Say 12 set.
yeah, noon of D-1, we have something called day ahead market, right? So I put here a spot for day ahead. Very clear what I wrote. Day ahead market. Okay, who clears that? Yes, it's the market operators. So there are different nominated electricity market operators in Europe. Can you name me a few? Yeah.
Markets or market traders, sorry.
Yeah, there are different market operators in Europe, and we call them nominated electricity market operators. They collect bids, and then there is one holistic market clearing, something called Euphemia, and then we clear market for the whole Europe in day ahead stage at once, right? So can you give me some names of the market operators in Europe? For example, Nord Pool. Yeah, Effects and others, right? So this is the market. So what I like to put here is that this is the realm of market operators who clear the market. Here I put TSO, transmission system operator, right? For example, the one in Denmark is Energinet, or in Germany we have 4 TSOs also, right? Or RTE for France, Tenet for Germany, for Netherlands. Good. So what other market we have? Yes.
Forward market.
Yes, forward markets. Where are they? Where should I put that box? So
they close
is,
at D-1 before the day ahead, and I think it's D-2 that they
no, forward markets. Well, they goes to Nasdaq, right? They are financial markets. Right? So here market operators. So I'm writing like medical doctors. Okay. So there are, I'm sorry, there are forward markets for long term. You can buy, you can sell power even for the next year, right? And Nasdaq in financial markets. So forward markets. So it's not by market operator, they are fully financial markets. Different story. Any other markets? Yes, Sanders? Very good. Intraday markets. So let's say that we are talking about this specific hour of the next day. So intraday market goes to up to when? It's different country by country, right? So for example, in Germany, if I'm not wrong, it's 5 minutes before the specific hour, right? So we have intraday markets. Intraday markets. Do you know what? Yes.
These the one that told that those 5 minutes are the continuous intraday.
Yeah, I was just about to say that. Okay, tell me, Theodore, what do you know about intraday market?
But we have the XP and the option.
Very good. So, the question to everybody, here it's an auction. There is a gate closure up to noon. You have to everyone submit bids. Then there is a market clearing, supply curve, demand curve, price done. But Theodore uses another word for intraday market, continuous market. What's that? Have you heard of it? What does it mean, continuous market? Is there a gate closure for a continuous market? No. No. Yes. Yeah. It's a matching market, right? So every moment you can come with a buying or selling order, and then you will find someone to be matched with. Right? There are a lot of stories there. So all the things that I'm talking about markets, it's not related to continuous, right? All the things that I discussed you need to have a gate code, and then you have a unit price. Okay, intraday market in Europe, it's a continuous, but recently they added some things. What they are? Have you heard of? Are you following news? Yeah, about the market. Yes, Theodore.
The IDA.
What?
The intraday auction.
Yeah.
IDA.
It does.
Yeah, intraday auctions.
Yes. So this is intraday continuous, but also recently intraday discrete auctions have also been added. So also we have 3 ID discrete, 1, 2, 3. It's a new thing, while still we have this continuous intraday. Is it clear? Okay, all of them still is handling by market operators. What else do we have? Yes. Balancing market. So in the real time, you need to have a balancing market. Who takes care of balancing market? Yes, sir. So now we are coming here. It's the balancing market. Right? So it's the TSO who takes care of the balancing. And then there are also a lot of stories in the balancing market, 1 price scheme, 2 price scheme, so forth, right? Actually, I'm teaching a master course just about all these things at TPU, not even talking about what I explained the last time. Okay. So do you mean that TSO only go to the balancing stage and do balance, or do we need more markets? Yeah, Sandra.
Yes,
ancillary service. There are a lot of stories here, buying different services, right? For different, the primary reserve, secondary reserve, tertiary reserve to buy capacity. So you buy their availability, the capacity, so to be able to activate them in the balancing stage if you need, right? So what are the terminologies for ancillary services in the TSO level for frequency? Yeah. What? Yeah, reserve. What kind of different reserves do we have? Yeah, well, that's correct, but usually in US, what are the European words? Very good. FCR, AFRR, MFRR, right? MFRR, manual frequency restoration reserve, AFRR, automatic frequency restoration reserve, FCR, frequency containment reserve. Even in Nordic side, because it's a different synchronous, we have even more services. For example, we have FCRD, frequency containment reserve under disturbance situations. In extreme situations, if frequency goes beyond 50.1 or drops below 49.9. Or we have something called FR, fast frequency reserve. So why I'm talking about this is because every product here we have, it has a market, it has its own market. And again, it's the TSO who's handling that. Now there are discussions of having also European markets for MFRR, FCR, AFRR, but in the activation level, right? Nothing. So just I'm telling you that when I'm talking about electricity market, we are not talking about one market. There are different products being handled by different entities at different points of time. Cool. Do we agree? Good. So also, as you see here, we buy reserve in a different market than electricity. The entities who handle that, they are different TSOs, market operators. While in the US, right? Joint markets, they have ISO who handles, who acts as both TSO and market operator. Yes, right? So we are talking about totally two different. Good. Yeah, if you want, you can check my slides for master course. They are online on my website. You can check, but there are a lot of stories. If I like to talk about this, I mean, we can easily talk about 5 hours about this. Right? Good. So I want to talk about equilibrium problem, what it is. None of you raised your hand, right? None of you knows what equilibrium problem is. Or Theodore, you knows.
It's a state that no party is incentivized.
Yeah, we'll talk. Very good. So we talked about this optimization problem, easy one, last lecture. So I have a simple question to you. So you are the market operator. You did your coding in MATLAB, Julia, Python, and you announced to everyone the market price is 20. I'm the boss, 20. You have to accept. Is it the case? Should everyone accept your decision? I'm trying to challenge that, right? So the question is that how to make sure all market participants, either G1, G2 from the generation side or D1, D2 in the demand side, they are happy with your outcome and they will not deviate from it. You may ask me, can they deviate? I will tell you, yes. If they find a way that if they deviate from your market clearing outcome, they will earn more, they will find a way to do it in one way or another, right? They can say, okay, there was an outage, blah, blah, blah. I mean, so we have to make sure that by principle, not by auditing, the market clearing outcome is something that everyone is happy with. Am I clear what I'm saying? So let's see, let's check it. So let's see what the optimization problem looks like from each market participant's perspective. Okay. So if you are a generator, what will be your objective function? Maximizing profit. You don't care about social welfare, I guess. And if you are from a demands perspective, maximizing utility, the value of electricity. Very good. So let's see how we can calculate the profit and demands utility. Do you agree that this is the optimization problem our generator G1 cares about? Let's check it for a second. What's that? Yeah, you know.
It's the revenue. What is the difference between the price and
Is this revenue or profit? Yeah, revenue is the income. Profit is income, revenue minus cost, right? Okay. So what G1 tries to do? Maximize profit. So PG1, it's the internal decision of G1, how much to produce. Lambda is the market price, but the market price, is it in the hand of market operator G1? No, it's the market operator's decision. 12 is the internal cost of the generator. So, for example, if the market price is 20, it means that the generator G1 will earn $8 per megawatt hour by producing every megawatt hour. And so far, let's say that this is the only technical constraints we have. Of course, you can add unit time constraints, blah, 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 blah. But for simplicity, this is the internal constraint of G. So do you agree that with me that this is the internal optimization problem of generator G? Do we agree? So So, and also the mu's are the dual variable. Okay? So do you agree that this is the one for G2? Is this lambda different than this lambda? No, it's a uniform pricing. One lambda for everyone. And here we don't have transmission line, so a lambda is the same for everyone. What about demand? What demand one does here? Maximize utility. It says that the value of using 1 megawatt power for me is 40. That's the value of power. I have industrial plant, and what I do. That's the utility. Lambda is the same lambda market price and how much I consume. And the same goes for heat. Okay. What item links these four optimization problems together? Yeah. Lambda. It appeared everywhere. Very good. Am I missing any constraint that we had before? Yes. Power balance. So exactly. So this is my power balance condition. That's is the constraint for any specific stakeholder or not? Is the constraint for the whole system? For the whole system. Okay. I have four optimization problems and one constraint. Is there any trick? I mean, now we have this lambda here before in the market, but when there is no optimization problem, then we can't define a dual variable, right? Can you tell me any mathematical trick that I can write this constraint as an optimization problem? Equivalent. Is my question clear? So if I write this, do you think this optimization problem in the red box and this constraint, do you think are equivalent or not? Peter?
It's equivalent because lambda is still the sensitivity factor.
Yeah. Do you agree that the objective function in the red box, if you take the KKT, you learn KKT, right? If you take the only variable is lambda, I'm talking mathematics. If you take a derivative over lambda, then the lambda will go away. Then you have this constraint. Are we okay? Good. So I'm writing the last constraint as another optimization problem, the fifth optimization problem. If you want, you can call it price setter optimization. It's a fictitious optimization problem. Okay. So a few questions to you. Lambda appeared in the four optimization problems. They are constraints for that one. While for the fifth one, it's a primal variable. Do you agree? What about this four, PD1, PD2, PG1, PG2? They are parameters here because, as you see, I haven't listed here, but they are variables in their corresponding optimization. Right? Can we say, can I solve these five problems separately? Can I solve separately? Non-iteratively, I would say. Can I do that? No, they are interrelated. So we cannot solve them separately and non-iteratively. So because they are related, and this is an equilibrium problem. An equilibrium problem is a set of optimization problems that you need to solve them all together, right? Of course, you can think of an iterative approach of saying that, okay, for given lambda, let me solve and then bring the values to here and then update lambda, and you can always do that, and we will talk about that, right? But if you like to solve it in one shot, you need to solve all of them together. this is an equilibrium problem, and this is also a game theoretic problem. And in economics, let's say literature, it's called also competitive equilibrium problem. Okay. So, do you think, well, we may have some discussions here. Do you think it's a non-cooperative game or cooperative? It's a game theoretic problem, right? Everyone tries to maximize their own profit. This is non-cooperative because everyone tries to maximize her own profit or utility, right? So we call it non-cooperative game. In cooperative game, I don't know how much you know, is that we solve one optimization problem all together. So in non-cooperative, let's say we are 20 people here, each of us, we solve our own, we are self-interested, and we only maximize our own, and then try to find equilibrium. In cooperative game, no, all of us together, we solve one optimization problem to maximize the profit of all of us. Let's say we earn $100 all together, but then the complex is afterward, how to split that among us based on our contributions, right? So then there are concepts like Shapley values, the Hill's value, how to split this $100 in a way that everyone is happy. But it's not the case here. This is non-cooperative. Every of us, each of us, we are maximizing our own profit. So we have to see that if there is a point, that if we reach there, everyone is happy, that's the point. Clear? Good. I'm thinking what I would like to say. Is it right time or not? I'll tell you in some minutes. This competitive game, competitive equilibrium, it's not something new. Maybe the first one is Kantrovich in 1939. He, in management science, which is still a very famous, he designed this competitive equilibrium formula. And then Samuelson and Arrow and Debris, they can, and all these gentlemen here, they got Nobel Prize in economics in different years for that. So there is a rich story behind what we are talking about. Yeah. So actually, I read this one. I mean, it's nice sometimes to read this old papers. And so whenever you do literature review, please don't stop in papers published the last 10 years. And go also the old papers. You can find a lot of things there. Also, if you like to learn more about complementarity and equilibrium models for energy system, this is a very good one. And in general, like a Bible, equal to convex optimization of both. But for game theory, this is the Bible. Okay, let me get back. So if we can solve these 5 optimization problems together, if we find a solution, how we will find a solution, we will talk. But if we find a solution, it will be a Nash equilibrium. And this is John Nash. Have you watched the Beautiful Mind? That's the movie of him, right? Also, he got Nobel. Okay. So Nash equilibrium says that no market participant can increase its profit by deviating unilaterally, means that alone, by acting alone, not in a group, from the equilibrium point. So it means that 20 of us, we are maximizing our profit. If there is a point that we realize, each of us, if we deviate just our own solution, we will not earn, then that's the equilibrium point. Is it clear? So it's a point that none of us should find a way to increase the profit. Even if my profit in this equilibrium is $1 while yours is $50, but if there is no way for me to increase my profit from $1, it's equilibrium. Clear? And what John Nash did, also you can read his papers back to 1950, I guess. He has a lot of proofs about uniqueness of equilibrium and how to. And if you check, then also you see that he uses KKTs, blah blah. Good. Yeah. Discussion. Something to teach you. There is something called Nash equilibrium and generalized Nash equilibrium, NE and GNE. First of all, do you know what the difference of NE and GNE are? Have you heard of? Okay, I can tell you. Equilibrium problem means that my decision variable appears in your optimization problem and vice versa, right? This is why all optimization problems are interactive. But if these variables only appear in objective functions, not constraints, then it's Nash equilibrium. Generalized Nash equilibrium says that my decision variable appears in your constraint, in your feasible space. Is it clear? Generally, NE is very easier to solve. You can easily prove uniqueness, existence, and uniqueness of your solution. GNE, in general, you can do nothing unless in specific conditions. For example, if the constraint is common for everyone. So, with this very brief explanation, do you think this is NE or GNE? It's a Nash equilibrium. Do you see anyone's variable appears in other one's constraints? No, it's NE. We love it. Right? Well, I'll not teach, but I think the exercise I have notes. There are ways that you can prove theoretically the existence of equilibrium point and its uniqueness. Do we like uniqueness of the equilibrium point or not? It doesn't matter. If 20 of us are gaming, if there is only one point that we can agree on, or there are 20 points, which one from the market perspective is better? A single one, right? Otherwise, if there are 20 points, then, okay, market operator will pick one, and then I will complain, no, why this one? Pick the other one that under which I will gain more. It's clear? Uniqueness. So whenever you design a market, think of that. I want a solution which is unique. It's a good property. Yes. Which one? I'll add. This is the one without transmission line. I'll show the version with transmission. No, it's all. I'll. That's very good. I promise I'll get back. But so far you agree this is Nash equilibrium. Very good. Yeah, I'll not talk about GNE. There's a big story also there. Also, if you read this book, there are a lot of stories about NE and GNEs there. Good. So, okay. Last lecture, I told about optimization problem for solving market clearing. We maximize social welfare with some constraints. Now I told you about equilibrium problem. Everyone tries to maximize profit utility. Also, there's a price setup problem that is actually the power balance problem. If you are the market operator, which one you will choose to solve? Will you try to maximize social welfare, or will you try to make sure everyone is happy? How many of you say, let's solve the optimization problem, maximize social welfare? We don't care if people are happy. Okay. How many of you say, oh no, let's solve the equilibrium problem, make sure that everyone is okay. We don't care about social welfare. Make sure that everyone is happy, no one will deviate. What do the rest think? What do you think?
Equilibrium.
You will go for equilibrium. Okay. Okay, you spoiled the story. So I'm telling all this story, blah, 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 to you to tell that these two things are equivalent. So when you solve this problem, implicitly, you're also solving this. That's fantastic. Then you have a market design that when you maximize social welfare, which is good, at the same time, you know that no one will deviate because there is a Nash equilibrium point. That's another market design property that we want. So far, I told you the existence of the the equilibrium point, its uniqueness, and then knowing that for our equilibrium problem, there is an equivalent optimization problem that does what? Maximize social welfare even better. But you know that the world is not that easy. On theory, there are many reasons that this equilibrium, this equality doesn't happen. I'll talk about it. Okay, but tell me, Lissandros, you told me that they are equivalent. How do you know that? You have a faith that they are equivalent, or how do you know that they are equivalent? Pardon me?
You derive the equilibrium from the optimization.
No.
Didn't you in the previous slide? You used the optimization formula.
No, I didn't. I said that this is the problem of maximizing profits for everyone, and I never started from that position.
Yeah.
No, that was a recap. The way the starting point for equilibrium problem was not the optimization problem. So, Lissandros, how do you say that? How can you convince us that they are equivalent? Otherwise, Andreas said, let's solve the equilibrium problem. And I'll do that. What did I teach you last lecture? Duality, KKTs, this stuff. You will leave here. Okay. How to show their equality?
And then maybe they're the same as the opposition.
Fantastic. Very good. Very good. You see, KKT is like that. How many optimization problems you have here? One. Drive KKTs. You will have KKTs. Very good. How many optimization you have here? Many. One per generator, one per demand, and one for price setter. In our example, we had 2 generators, 2 demand, 1. So we have 5 optimization problems. Derive KKTs of all 5 put together. Compare this set of KKTs with this set of KKTs. If they are equivalent, then these two systems are. So that's exactly what I'm gonna do. So from each box, we drive KKTs. Now we put all KKTs together. In mathematical programming or mathematical science, we call this mixed complementarity problem. It's the set of the KKTs of different optimization problems. It's MCP. It's straightforward to solve. I mean, have you heard of any existing solver to solve that? For example, PATH. It's a solver to solve mixed MCP problems. So what we drive, we have only one optimization problem. So KKTs. Here we have a set of KKTs. So we check these KKTs with this set of KKTs. If they are equivalent, then this works. Okay. Good. This is the equilibrium problem of our example, right? So G1, G2, D1, D2 price setter, right? So let's just start with the equilibrium problem and derive KKTs. Without deriving the Lagrangian function, can you help me to derive the KKTs? Or let me do that. So now first we write it in a canonical form. So instead of maximize, we write minimize. minus PG1 lambda minus 12. PG1 minus is less than or equal to 0. Mu bar G1, PG1 minus 100 is less than or equal to 0. Corresponding dual variable is mu bar G. Very good. Then we write the Lagrangian function, which is a function of PG1, mu underline, and mu bar, which is equal to minus PG1 lambda minus 12 minus PG1 mu G1 underline plus mu bar G1 times PG1 minus 100. Do you agree? And then we derive KKTs. So Lagrangian derivative with respect to the only variable, primal variable we have is equal to minus lambda plus 12 minus mu underline plus mu bar equal to 0. Correct? Then we have two inequalities, so one complementarity each. So PG1 minus, this is less than or equal to 0. Corresponding dual variable, non-negative, their product equal. And the same for the next one. Right? So if you drag, this is the KKTs of chapter 5 optimization. Please check it for a second and see what we do. Is it clear what I'm doing? Yes? So now this all KKTs together, it's MCP, mixed complementarity problem, right? If I solve this set of equations, I'm solving the equilibrium problem. Clear? Okay. So remember, this was my optimization problem. If you derive KKTs of this optimization, it will be exactly the same. I leave it to you to get home, but it will be exactly. Which is fantastic. So equilibrium and optimization problems, they are equivalent because their corresponding KKTs are identical. And both equilibrium and optimization form, they have a Nash equilibrium solution. How do we know there's a Nash equilibrium? Because the optimization problem has an equivalent equilibrium, and that equilibrium is Nash equilibrium, is NE, and there is a Nash equilibrium for that. So there is a Nash equilibrium for optimization problem. So if you like to design electricity market, for MFIR, for FCR, for forward market, for I don't know, whatever, balancing market. So what properties they have to look for? What properties so far we discussed? Yeah. Well, uniqueness of the solution. I mean, it's important. And also its existence, right? The solution should, that there should be a solution, and that solution hopefully exists, is unique. What else? There should be a Nash equilibrium. And luckily, our Nash equilibrium is aligned with maximized social welfare. That's amazing. We maximize social welfare, and that's the Nash equilibrium. Tomorrow, in the next lecture, tomorrow, I will add a few more properties. So please, I mean, whenever next time you design a market, just make sure that the properties are there. If not, that market design is not good. The industry, the practice will not adopt it. Okay. So that's a teaser for a lecture tomorrow. Right? So conclusion, we are not finishing, but so far. This is what you learned last lecture. Now I brought back tape. Right? Now this is the version with transmission lines. Okay. This is the one with optimization problem, maximizing social welfare with transmission line. I'll get back to this. Wait. This is the one. This is the one with the KKTs. So you can derive the KKTs of the optimization problem here. So we can write optimization problem, the primal. We can write optimization as the dual problem, the last exercise, the exercise of the last lecture. You can derive the KKTs. You can derive its equivalent equilibrium. All of them, they are equivalent. It doesn't matter which one you solve. So now I have a challenge for you. Exactly what you want. Now it's the time to discuss. Now we have transmission lines here. So how can I write? Please don't check the slides if you have it online. So, Sanders, you saw my slides before, so maybe you can spoil again if you want. I'm kidding. So, I have the transmission lines, right? Can I write still an equilibrium problem? Remember last time we had equilibrium one optimization problem per generator, one optimization for demand, one optimization for price, etc. Now I have this new constraint of transmission line. I have power balance quality per node. So can I still write an equilibrium problem? Can I? Any idea? So if I get back to this problem, here I don't have transmission line constraints. If I like to add transmission line constraints, where should I add? Yeah, listen.
Power balance.
You will have something extra here.
Yes.
You will have
For each,
KIOS.
for each node, you will have the different.
Okay, what about the transmission line constraint?
The constraint with the transmission line, the power
Yeah.
balance, is transferred from.
Yes. So also you will write constraints here. Then you kill NE. Then theta appears in constraints. Then we are screwed. Then NE is gone. We have GNE. We don't like it. But we have transmission line constraint. Flow should be less than 100. Where should I put that? People online also can answer. You are very negative online. You're lucky you're not. Why you are not thinking of adding extra bucks? Why you want to put everything there? Can I?
Price setters.
Yeah.
More of the dual value in the other lines.
Okay. You're getting there. Okay, now let me reveal the answer and then challenge you. You already saw one optimization per generator, per demand, price setter. Now I have something new. And I call it profit maximization problem for transmission owner. Can you check if you agree with this? Please think for a minute. No problem. 2 minutes you have to think. Yeah. First, I'll also tell you, if you drive the KKTs of this problem, it's exactly the same as market clearing problem optimization with transmission line. Good news. One. Second, is it NE or GNE? If you accept this structure, if it's NE or GNE, NE, there is no constraint there is a variable from anyone else. Here, this box, the only variable appears as theta is the internal variable. Only internal variable appears in the, so every box in the constraint has only the internal variable, not external variable from someone else. So it's NE, good news. If you derive the KKTs of this equilibrium, it's exactly the same as market clearing. Well, again, the other good news. But how to interpret this? You have 10 minutes. Or no, until 6, great. Okay. Let's start with the other easy boxes. The first two boxes, generator and demand. Do you agree with me? You agree, right? Nothing changed there. The price setter. You agree that if we take a derivative or KKT and take it Lagrange derivative over lambda, this is our power balance equality per node. So hopefully with the first two boxes and the last box, you are with me. So the challenge is the middle box, right? What is that? TSO. Yeah. Who said TSO? Right? Are you saying TSO is maximizing? Pardon me? Well, I don't have any maintenance here. Yeah, but it's not maintenance. It's a trading problem. Pardon me? No. Okay, let me tell you. This is flow from M to N. No, it's the flow. How much power flow goes from M to N? It's megawatt. Based on DC power flow, this is F M to N.
So the intuition should be that the cheaper node, it transfers power to the more expensive node to drop the price of that node. And that equilibrium, unless constraints are met, these prices should be.
Very good. That's good stuff. Let's say that here is bus N. This is bus M. This is a flow from Fn to M, right? Say the price here is 20, and say the price here is 30. Why? Because this line is congested. If it's not congested, the prices will be the same. I'm just giving you an example. So this transmission system operator, let's say, how much it pays. So you can say that the transmission system line, if you like to see it like that, it buys, instead of FNM, let me call it 50 megawatt. So now we are buying 50 megawatt at price 20, transferring it to the other node, and selling it at price 30. There is a profit there, right? It's a trader, special arbitrator, if you want. So what's the profit here? 50 times 30 minus 20. $500. So you are selling at price 30, you are buying at price 20. And this is exactly that. So, and of course, this is the constraint. And still we have NE, as I said. But the question is this. When I'm solving a market clearing problem, you can call it TSO, transmission system, or whatever. Are they profit? Is it a profit maximizer? So, Lissandros, you wrote a unit commitment to a TSO. Are they a profit maximizer? Apparently they are. And they are. So do you know what this money is called? No, transmission fee is external thing. You say that you are using this, you have to pay this. No. It's called congestion rate. Congestion rate. So when do we have different prices here? When there is a congestion. If there is no congestion, what this profit will be? 0. So now I'm even challenging you more. Do you mean that TSO wants to have a congestion? If there, well, I mean, if there is no congestion, the profit is 0. So you want to have a congestion? Yeah, I mean, this equation says that you want to have a congestion because you are a profit maximizer. No congestion, no congestion rate. Congestion rate, sorry, congestion, you have a positive congestion rate. So the answer is yes. By theory, TSO is a profit maximizer and TSO earns congestion. But then there is the legislation, governmental watch to make sure that they are operating the system for security, not for profit. Are they earning? Yes. Are they getting congestion rent? Yes. But they are not how to say, allowed to schedule the system to maximize this profit. It's a by the way money. It goes their pocket. Actually, it's a good money. But then they're obliged to use it for transmission expansion or for society. So TSO should bring back that money to the society. Otherwise, if you have a free market, yes, TSO or whatever you want to call transmission asset owner is like generation asset owner. Why they should not earn money? They're also providing assets. Am I clear? So in US, there's something called FDR, financial transmission rights. I don't know if you heard of that or not. So for example, if you are a demand at the price, note that the price is 30, I mean, if you are a demand here, you will not be happy. The generator sells at price 20 and 10 goes to transmission line and you are paying 30. Then you can buy FDR rights from the transmission system. So whenever congestion rent comes, the transmission system owner pays you back the $10, then you see the price of 20. So it means that you go and buy a share of this transmission line financially, not physically. So FDR, financial transmission line rights. FDR, financial transmission line, comes from that. As far as I know, in Europe, we don't have such a thing. So what happens? Yeah, so they get money. For example, in a zonal setup, the two TSOs, they have to split money. But they're obliged to see it like tariffs and bring it back to the society by, I don't know, maintenance or whatever. But it's very interesting, right? See that. So if you let a TSO, they want to make sure always there is a condition. So that's a very controversial, result you see. I can tell you one more thing. So let me find, yeah. So in Denmark, we have feeding zone DK2, feeding zone DK1. Here there's a SE Sweden 4, right? Here we have Germany, the feeding zones, right? They are connected to each other. Then we have Norway's, blah, blah. Now, I don't know if you heard of it or not, there is going to be energy islands. And then there were a lot of discussions, and eventually ENZOE and Danish authorities, they agreed to have it as DK3. That will be the third. So having DK3 was decided. Then there was a lot of discussions. So then, okay, this is an island, and this is the mainland Denmark. Sorry for my not good writing. They should be connected. There are a lot of discussions between Energinet, which is the TSO in Denmark, and all developers here, like Ørsted or Vestas, who are gonna build wind turbines there on the capacity of this transmission. Why? And I'm not sure it's still there, as far as I know, but not wrong. Still they are fighting. But there is no, okay, fight maybe it's a strong word. So they are debating a lot about the capacity of that one. Why, Theodore?
Does the investors want the bigger capacity so they gain more money and the TSO wants the line to be congested?
You're getting. So remember, in DK3 will be energy island. There will be no demand there. There will be only wind turbines. Maybe there will be hydrogen electrolyzers. That is still under discussion. So if the line is congested, what the market price in DK3 will be? Simply zero. What will be the price in DK2? Whatever, 50. Who will get all the 50? Only an Energinet. Ørsted developers, they will earn zero. So does Energinet want to invest in a big capacity? No. But if then Energinet does that, then Energinet will earn nothing. So then Energinet says, okay, if you want, then you have to contribute in the cost of that transmission line.
Everywhere where you have.
Oh, yeah. Yes. But this is a bit extreme case because you have only wind, no demand. But so you heard about European market reforms recently, right? How to support renewables, blah, blah, blah. One of them is, for example, CFD, right? Contract for differentiation, blah, blah. There is also another big keyword there. Have you heard of that? TAG, TAG. What's that? Transmission access guarantee. Transmission access guarantee. It's a bit like FDR, but it's not FDR, something similar. It's also a debate. So there are also different types of TAC people or politicians or they are discussing. So Ørsted or developers will say, okay, I will not invest in this energy islands unless you provide me TAC here, a guarantee that I will have access to transmission. Right? So what kind of TAC Energinet should provide to developers, blah, blah. All of them, they are still under discussion. And yeah, I mean, the debate is that strong that even we don't know if the energy island will happen or not. So I'm trying to say that the problem is serious. But all these things comes from the congestion rate. Yes, TSOs earn.
Argument about the island. Basically, all this money that.
Wow, you see this? I can't read this. It's very ugly.
This is based on the assumption of non-cooperative behavior between the energy producers. Because otherwise,
everyone tries to maximize its own profit.
but in that case, they are get exploited by the TSO. Then the optimal, the natural equilibrium would be to like.
Do you want to go and tell the CEO of developers, let's go and solve one optimization problem and then solve Shapley values, blah, blah. It's not going to work. Everyone tries to maximize their own profit, and then the share owners will see your profit. I mean, that's how it works. I'm not saying there's no other solution, but how the practice works today is like a lot of legal discussion. So again, I'm trying to say that whenever, well, we can be very extreme in our extensions or whatever, but if you like to have a research that hopefully Energinet or they will adopt it as soon as possible, we have to stick to the ground they are playing. If I could convey my message.
With large storage, storage would might change a bit.
Oh, yeah, storage. Storage is a player. Electrolyzers are players.
Yeah.
I fully agree with you. But today, in the start, we don't have it.
I will pressure TSOs lower, I mean,
I fully agree. Good. So these tax things are interesting. So if you're looking for a research area which is not crowded at all, while if you do something nice, it will be adopted soon. Hack is a good. Yeah. So we learned that okay, we have an equilibrium problem that TSO or acetone or whatever they maximize the profit. I mean, you see TSO, you can see TSO in the same way as the storage. Why? Or how? The storage does trading over time. TSO or system or transmission system owner, they do trade over space. It's the same thing. The same concept. Right? Good. Where am I? Yes. Okay, what we learned simply is we have three forms of market clearing, optimization, equilibrium, MCP, which is the AKTs. All of them are equivalent. Have you heard of words externalities? Externality. Yeah. Can you tell me examples of externality? Pardon me? COVID. No, externality, yeah, of course. But externality means anything, any payment, any that comes outside the market. Or it's not a market-based thing. It's exogenous things to the market. Have you seen any things exogenous here? No. By exogenous, I'm not talking about the capacity of the line. No. Something that changes the profit or utility of people. Yeah.
You don't have the prices.
Yes, exactly. Very good. Very good. So if you have a constraint here saying that lambda should be less than or equal to, for example, 1,000 euro per megawatt hour, that's an externality. You're pushing something that doesn't need to be there. But of course, there are reasons that you put that. But we call it externality. And of course, it will change social welfare, blah, blah. Other kind of externality. For example, tariffs that you pay renewables outside the market, right? So then they earn lambda plus something, or grid tariffs, or anything. But the other externality is, and I'll talk about tomorrow more, is the strategic bidding, right? So for example, here we assume that lambda is not changeable by any generator. Am I clear what I'm saying? There might be smart generators saying that lambda is a function of my production. I can change it. This is also an externality. See what I'm saying? This is strategic bidding, right? So why I should assume that lambda is given? What if I know how the market works and manipulate that? If especially I'm a big supplier or a big demand, right? So there are many things that if you add externalities, this equivalence may gone. You may fail. And if it happens, if our system, the optimization and equilibrium, they are not equivalent anymore, it means that what? People may deviate from market clearing outcomes. Right? Then what we say? We say market fail. So the term market failure, I don't know if you heard of that or not. I mean, some people, they use it in a wrong way, but market failure means that our optimization problem maximizing social welfare has no longer an equilibrium problem, which is equivalent. Then you can say market fail. because there are some people who can deviate to earn more. Okay, again, when you design market, please think of all these things. There are important things, right? Not important, even fundamental. Good. If you took my course, I would ask you to write these exercises, but now they are optional if you want. So if you like to do some stuff fun later, after this week, for example, you can think of exercise number 2. I mean, we solved equilibrium problem without any iteration, right? By putting all KKTs together. Other approach is iterative approach. For example, based on this type of pattern mode process. It's easy. So if, let's say, every of you are reacting to price, I'm sending you a price to solve your own optimization problem and send me back your production or consumption. Then I see if there is a match between total production and consumption. If not, second iteration, I update price, I send you back. We do this until we come. So I have my lectures online on YouTube. You can check. For example, you can use something called Lagrangian relaxation to do this. But you will get convergence if your problems are quadratic. If it's linear, it will not converge, likely. Then you need to add some quadratic regularizer. Then you will move. Then you can use something, for example, ADM or consensus ADM or something. So you can check my videos online, how we can solve a market clearing problem iteratively. No one does that. I mean, I'm not aware of any market design. I mean, there are millions of papers talking about market design iteratively, and they are very fantastic works. But I'm not aware of any market in reality, even local markets or global markets, whatever, that they solve market clearing problem iteratively. I'm not aware. Maybe you are, but I'm not aware. I mean, if you go and talk to Oracle, let's solve it iteratively. Thank you. Fine. Yeah, but that's how it is. Sorry, but then you can think how to. I mean, if you like to do something good for your PhD thesis or whatever, I mean, if you solve if your problem is a equilibrium problem, you have to think of uniqueness and existence of your equilibrium point. Then, for example, the famous book I told you, there is something called principle of symmetry. You can drive your KKTs, the system, you can drive the Jacobian matrix, you can see if it's symmetric or not. If it is, oh, sorry, what else is? You can drive the KKT systems, you can see if it's your matrix, Jacobian matrix is symmetric or not. If it's symmetric, it means that your equilibrium problem has definitely an optimization problem, which is important. But then also you can check the Jacobian matrix if it's a positive definite or not. Then you can argue if you have a unique solution or not. If it is positive definite, definitely you have a unique solution. If it's not, you cannot say anything. Then there are other things like degree theory or whatever that you can also try to see if you can. Yeah, this is the number 3 and 4 I just. So it's not something that I will drive for you. I have some papers that we use that, but you can, if you want, you can check. Yeah, you can check also the monotonicity property of the Jacobian matrix for the uniqueness, for the proof of the uniqueness of your. Yeah, that's all. We have 15 minutes. We can have a discussion if you want. I think I talked enough for today. So. If you have questions, please, you can have it.
Do these principles apply also to stochastic
energy?
This principle also apply on stochastic energy market there because.
Yeah, very good. I can talk with them. So it's a good question. Let me get back to, oops. Yeah. Let me get back to our, I like to, yeah, explain it. Yes. So what Theodore is asking is, yeah, let's say that, for example, this generator is wind farm. So I don't know what my full production will be, but it's, for example, something which is uncertain. For example, S is the index for scenario, for example. So I don't know, it could be 100, it could be 50, it could be 60. I don't know in advance how much wind output. Then what happens is that my production is stochastic. Then since, oh, also we have a price setter problem, right? Then PG1 is stochastic, then also lambda is stochastic. If lambda is stochastic, other all problems are stochastic, right? One is stochastic in one optimization problem, it propagates everywhere. Right? So the other question is that, can we write it in a stochastic form? I mean, let's say stochastic scenario-based program, but also you can do it in a robust way, distribution robust way, I don't know, interval optimization, or chance constraint, any form of, yeah, you can. Let's look at the simple way, scenario-based program. Yes, you can write all the problems with the stochastic. But then what will be your objective function? Maximizing what? Profit? Not anymore. Expected profit, right? Or it will, or it's up to you, or it could be maximizing CVAR in the worst quantile or whatever. So what will happen is that, yes, still you have equivalent optimization. Still you have, what I say, yeah, the good properties there. I told you, yes, all of them you have. What you don't have is what I will tell you tomorrow. So tomorrow, okay, a bit of teaser, we will discuss that. Also, you need more properties. For example, know that profit of every player in the market will be non-negative. If I know that there is a market that I may lose, my profit might be minus $100, I will not enter that market. It's too risky. So one of the good properties is that you have individual rationality, or also you can call it cost recovery. People will be able to recover their costs. So when you add the stochasticity, then you are not maximizing the profit, but you are maximizing the expected profit. Then you have cost recovery only in expectation. Then you will tell people, I promise in expectation, which could be 10 years, you will recover your cost. Thank you, but maybe until 10 years, maybe next year at that time, right? So you will not lose, but you will weaken your market fund. So that's one big reason why stochastic market trading is not that, because everything is in expectation. That's one reason. The second reason is that, well, I don't tell you about merit orders. You will lose merit order. I can explain you later. The third reason will be scenarios. Who will generate those scenarios? How to agree on scenarios, right? So there are many reasons that I don't think stochastic market theory will be adapted. I love stochastic programming. I did a bit in my PhD, but then after when I work with industry, I realized, okay, too far for them to be adapted. So no, I don't think stochastic market theory will be adapted. These properties, yes, hold. Other properties that we will discuss tomorrow, only an expectation. It's not an.
They have a risk position, but not the same as any other market.
Yeah, financial market, yes. But are you going to ask, I don't know, a big developer, come and invest 10 million euro or whatever you may lose? Of course, they may enter the market or may not, but definitely will be less attractive. Yeah, we already make everything's in a market form to attract more people to come and invest. It's not a financial market, it's an electricity market, it's essential things. Yeah.
Cars.
Yeah.
They have
If you talk to your regulator and convince them that, okay, let's make it more risky, I don't think they will accept. I mean, it's a political decision. I don't say there's something wrong with it, right? In my experience, it will not work politically and policy-wise. I don't think it's theoretically possible, yeah. Yeah, but I don't think government or whatever, they will not treat electricity market in the same way as finance.
Question about the differences between the US and the European market. In the US, they consider the unit rate, but in Europe, they won't. However, how the producers conventional generated units can ensure that the bits that they submit in the European markets, they satisfy the bid. Because they,
In Europe, you mean,
yeah, in
their
Europe,
problem. Your constraint, your problem.
okay, so it leads to power imbalances and then this.
What happens is that what happens is following. You submit your either regular or complex bits. By complex bits, I'm talking about block orders, whatever. Which, by the way, adds integer variables, which is not, I'll talk about that tomorrow. Then there's a market clearing. Then the producers should announce their respective TSOs how to disaggregate their bits. So what, for example, they bid in the electricity market says, okay, I'm going to produce this, but they don't say which generator. It's in aggregation level. But after market clearing outcomes, they have to disaggregate and tell the TSOs, that's how I like to fulfill my bid. And if they can't, they have to tell TSO, okay, I can't, or they should go intraday market and satisfy their bid. And then TSO starts running ACOPF, whatever, to see if the system is feasible or not.
I understand that for US it's very complicated process to solve it.
Yeah. I mean, in Europe, we have a lot of simplicity, especially because of the bidding zone. In US, you put every constraint directly in the market clearing problem, including unit nodal structure, network structure, topology, unit commitment. So when you solve the market clearing problem in US, you don't need much redispatch. Everything, all the constraints are fulfilled, but of course the price, I don't know, here might be different than price in other neighborhoods because of the congestion or whatever, right? Also, unit commitment problem, constraints, they bring some problems that I'll discuss tomorrow. I mean, some people, they may lose money. In Europe, we don't have that. Theoretically, of course, if you put all constraints in in the optimization problem, it's better than restoring those constraints later exposed. You need to have a redispatch, right? So theoretically, definitely US markets are better. But why do we do that like that in Europe? Again, I think I mean, right now we have in the whole Germany, we have one price. If we split Germany in two zones, the price in north will be half of the price in south because of all the renewables in north. So is it easy to convince for politicians, or is it easy to tell them that, okay, the price here or there, it's half because we don't have, it's tougher. So I'm trying to find the right words to say that, right? So what eventually it has been decided, saying that, okay, let's have one price for the whole country, but then we pay hugely for the dispatch. How big is that? What I heard, now it's recorded, I don't know the numbers I'm saying is, but I heard that, for example, last year, the redispatch cost in Germany, just after market clearing, just to restore constraints that we haven't reflected in the optimization problem, was about 10 billion euros, while it was like 1-2 billion euros 10 years ago, and this is increasing inflation, right? So this is what, do we want to have one price for the whole country, or do we want to have a big dispatch? So that's something that, again, I don't think there is a right or wrong decision. It's a choice. But theoretically, yes, if you put all constraints in the first place in the optimization problem, then you're okay. Then you don't need to do out of the market exposed corrections. But then you have to accept that you have different prices everywhere. Is it easy decision to take? I don't know. Did I answer your question?
Yeah.
Okay. Any questions? Yeah.
The population you showed up with the transmission.
Yes.
I don't remember the name you gave the problem. That's why
Transmission. I called here transmission owner. It could be TS
I
or.
was just about the losses.
Oh yeah, I haven't. I didn't put it. If you want, you have to put it.
Yeah, exactly. So, for example, if you have the network with match or not, but each line will have different loss.
But that's the problem. When you adopt the most basic version of DC power flow, you don't have any. You lose a lot. You lose many things, among others, lots. There are ways, I guess, of the variance of DC power flow that also estimates losses. Let's say.
Is it worth it though? Making the models more actualistic, or
as long as you keep the convexity, yes, and as long as you make sure that field optimization problem exists, yes. But I'm not aware of any market that go beyond this. Even in Europe, we don't even have this. We have simply
just the research.
Yeah.
Let's say
yes. I will tell you two things. Then first, make sure this is convex. One shot, because many approaches, they're sequential approaches. So keep one shot. I also make sure that the equivalent optimization still exists. Yeah, but I can already tell you that most likely then it's very possible that the price per nodes might be different, though if there is no congestion. I think it's a good research. Sure. Yeah, you can play in many ways with this.
So time is not a factor here.
Oh yeah, also you can add time. Yeah. If there is no intertemporal constraints, it's okay. If what kind of intertemporal constraints we have? Let's say ramping, then yeah, it appears in the generator's constraint. If you have storage, then you have extra bucks for the storage. And of course, if you have any time of intertemporal constraint, you have to add index T or time. And of course, you have to solve it for the whole. Just you can easily make the problem with some. But it will not kill NE, because constraints will be internal constraints of one of the boxes. So it will keep the Nash equilibrium problem. It will not make the problem GN. Yes,
regarding to the DC pipeline or DC,
yeah.
Which actually the power flow is from the initial contract.
Yeah, you can do that also. Also, you have to see if the DC line owners and AC line owners, they are the same entity or not. It's likely yes. Then also in the same way that you can add losses, also you can add DC connections. So this is just, the basic. You can make it complex in any way you want. So if you like to design a market having HVDC lines, I would start from here. First, I would formulate equilibrium problem. Then I will try to find its equivalent optimization problem. So my starting point will be from here, right? So think how to add anything you want, loss, HVDC lines, whatever. How to add it here, keeping convexity, keeping having coolant optimization. As long as you keep these two things, do whatever you want. Yeah. Good. Thanks a lot. Then see you tomorrow morning.